Hello and welcome to the 14th lecture in our comprehensive course of Data Science, Machine Learning and Artificial Intelligence. This is 14th lecture of chapter 19. Now, earlier we did three continuous probability distributions. That is these three: uniform, exponential distribution and normal distribution. These are continuous distributions. Now we want to do these three. These are discrete probability distributions. Okay. So let us start with the first amongst the discrete probability distributions. So here, this is binomial distribution. Now, a very well-known example of that binomial distribution is the coin toss experiment. However, you should understand one thing, that there is a difference between that coin toss experiment and coin toss trial. If you do the coin toss for the first time, then that has 50-50% chance of getting a head or getting a tail, right? So we say that the probability of having head, say head is my success event, then head is 50%. But that does not mean that if first time tail came, then in the very second attempt you will get head, because probability is 50-50%. So if one was tail, next must be head. No. Each coin toss process, that is called one Bernoulli trial. And if you do hundreds of or thousands of such coin tosses, then that is called one Bernoulli experiment. So this diagram shows one such Bernoulli experiment in which we do total around 12,000 sets of 50 coin flips. Now, are you understanding what I'm telling? That means one experiment is tossing the coin 50 times and noting down how many times head came and how many times tail came. That is first experiment. Then do the same experiment again, toss the coin 50 times, note down how many heads are there, how many tails are there. That is called second set of experiment. So do around 9,000 such sets of experiment, or even more, 12,000 such sets of experiment, and then plot how many heads came in 50 coin flips for each set. Then you will find that the distribution would be like this. Now, it is possible that you may not get these in the first experiment itself. Okay, first 50 coin toss itself. You may not get these. You may get these in the very first coin toss. But ultimately, when 12,000 sets of 50 coin flips are completed, then you will find that the minimum number of heads in 50 is around 0. So that means, or maybe 1. So there may be some extremely rare experiment in which you will find that only one times head came and 49 times tail came. But that is extremely rare. In fact, here it is shown that the events were less than 35. So less than 35 or greater than 35 on this side. These are pretty rare. That means here, for example, these events are pretty rare, or they are less, okay, less likely to occur. However, if you repeat the experiment of 50 coin flips 12,000 times, then you will see that ultimately it might be possible that in the first experiment you get this, but in third experiment you get this, then in fifth experiment you may get this, then in 1129th experiment you may get this, but ultimately when all 12,000 sets of experiment in each of which you will do 50 coin flips, they are completed, then you will get this kind of graph. And this graph says that now I can say that the mean of this graph is here at 25. So that is the meaning of word that the probability is 50%. That among 50 coin flip, on an average, 25 times, on an average, 25 times are heads and 25 times therefore are tails. So the probability is 50-50%. So this on an average word is very tricky. Okay. And as a result, whenever you read this kind of statements, there is some term called statistical jugglery. So whenever people want some item, news item, or some post on the social media to be convincing, they add their own statistic without doing any experiment. That is a kind of dishonesty. But they do that, say, and they add this word on an average. Now it is very difficult to test that on an average. Even for simple experiment like coin toss, you can see where there are only two outcomes possible, head or tail. You have to do fairly large number of experiments. Okay, so suppose somebody wants to circulate a false stock tip. Okay, like XYZ company's stock on an average gives 20% upside in 6 months on last maybe 10 years data. Now in last 10 years data, think how many 6 months period came. So that is around just 26 months period. So is that a sufficiently large number for giving such accurate prediction for the stock price that on an average it gives 60% upside as per the data of last 6 months? Okay, no, it is not. But such tips you might have read circulating. So always treat these things with proper skepticism. That is the difference between a person who is trained in data science and a person who is a layman. A layman does not know anything and believes everything. In fact, most of our beliefs are just borrowed from other people without doing any independent scrutiny, because we do not have the tools to do independent scrutiny. So the biggest benefit of learning data science is it makes you very rational person, and it makes you a person who examines everything from maybe two, three angles or more angles, scrutinizes things, and does not believe anything at its face value. And that is a very good ability. And even in your daily life, that ability will help you. Whether as a data scientist you will get that thousands of dollars of salary per month, that is a different thing. Most of the people get it provided they become excellent at their craft, and that requires a lot of long learning. But that is a totally different thing. But I can guarantee one thing, that after becoming data scientist, you will become much more rational in your attitude towards life, and your life decisions would be far more rational. Okay, now this success in classification task is another example of the binomial distribution. Actually, this is a classification only, that you are tossing the coin and you are classifying among the two possibilities, that whether head will come or whether tail will come, right? But one example is this, which is a very famous example in data science, that we're predicting whether email is spam or ham over n emails. That also follows binomial distribution. And earlier we had one such line in that email spam ham example we had taken earlier in one lecture, in this chapter only. So we said that 10% of the emails are spam emails. That means that if you take a large number of sets of observation, again in each experiment or each set, suppose you take 100 emails, okay. So this one set, just like here one set is 50 coin flips, similarly here one set is testing 100 emails for spam or ham. Then it is not necessary that out of 100, 10 will be detected as spam in the very first go. No, because you have to repeat, take another 100 emails, then take another 100 emails, then take another 100 emails, take another 100 emails, and so on, and ultimately repeat the whole experiment maybe 10,000 times, 12,000 times. So try to understand how many email samples you will require. 12,000 multiplied by 100. Okay, so that means you will require around 1,20,000 email samples. So that is the reason why all over world big data has become so much rich, because it is found that ultimately data science is nothing but probability, and probability becomes more and more accurate, because that word on an average 50% are held, that becomes more and more accurate if the number of sets of experiment are very large. So therefore the larger the data you have, more accurate will be your predictions by a model which is trained on that data. Of course, if the data is small, say I said that 1,20,000 email samples are required, but what to do if you have only 12,000 email samples? Then there are ways to do it by using k-fold, 5-fold and all that. We are going to discuss that. So smaller samples also can be handled, and they can give as accurate result as 1,20,000 emails. But for that you have to use k-fold cross validation and so many other techniques. So we will see them when they are coming. But the point is that instead of 1,20,000, 12,000 is fine. But if you have just 100 emails and you try to find out that sentence said that on an average 10% of the emails are spam emails. So in my sample of 100 emails, 10 emails must be spam emails. Then that may happen, may not happen. It is possible that 20 are spam emails, or it is possible that only 2 are spam emails, like that. But if you take a very large number of email samples of 100 emails, and if you do that experiment, repeat that checking. What is experiment here? Checking 100 emails for spam. That is one set of experiment, and if you repeat that set for 12,000 times, then it is possible that out of 100, 10 are spam email and 90 are ham email. Okay. Now then, geometric distribution. So geometric distribution is also a kind of discrete distribution only, and it is somewhat similar to binomial distribution, but its focus is different. In binomial distribution, our focus is on how many times an event becomes successful over a large number of experiments. So how many times head will come? That is our focus. While in geometric distribution, it is totally different thing. That how many attempts will be required before I get my first head, or maybe before I get my first tail. If that kind of question is asked, then you will use geometric distribution, and many examples are given. So as you take these examples, things become clear. Okay, this formula for mean and standard deviation, they are not important. Just I have given as an extra information, because throughout our course, our approach is clear, and that approach you will find wherever you go to work in any company, that they will check whether you have this concept of binomial and standard deviation and mean are clear or not. But they will not ask you to take a pen and paper or pencil and notebook and calculate standard deviation or calculate this probability using equation, right? They will ask using a program. So we have to programmatically find all these probabilities and everything and use that in some practical application. Now here in this formula, this nx is written, that is actually this only, cnx. Okay, so some books write combination this way, C combination nx instead of R here x, but some books write the same combination this way. So combination nx, okay, in a large vertical parenthesis or a big vertical bracket. So these are both the same things, just for the information. Now this geometric distribution. So let us take one example. In A/B testing, now this A/B testing is very important thing, particularly for the online shopping portals. And suppose you are changing the design for your online shopping portal, and you have hired two UX developers, and your aim is very simple. Whenever any online shopping portal is designed, first entire customer journey is mapped on a diagram. Okay, so what is done is what customer will do to finally make the payment. So first he will log in. Second, he will browse for an item. Third, he will select an item. Fourth, he will choose his payment method and delivery address. Fifth, he will make the payment. Then we say that it is a success, conversion. But sometimes, most of the times, the person will log in, will visit one or two items. Then he may find that no, this is too costly, or maybe it is not meeting my requirement, or maybe he just finds the user interface is not to my taste. Because nowadays, customer is the king, and uh, even the biggest company of the world, they have to take care of customers' likes and dislikes. So he may just log out saying that no, this user interface is, I find it clunky. So what you have to do is that two people are asked to map that customer journey using a user interface which goes from one window to another screen to another screen to another screen like that. And they have designed their website in totally two different manner. Now half of the customer are shown one website, say website A, and another half of the customer are shown another website, say website B. And then it is tested that a same kind of user who has entered the website, logged in the website, and who is looking for a laptop is successfully converted in how many visits with design A, and how many visits means how many screens does it travel. Maybe it goes back and forth many times, and so how many screens does it travel before making a successful payment. And second thing, that what may be the rating does he leave for his shopping experience, because you have seen that kind of survey comes immediately at the time of checking out, that just please rate your shopping experience on a scale of 1 to 5. So just 1 second is required, you have to rate. So if two people are there, and one has tested the A version of the website and another has tested the B version of the website, the person who tested A version of the website navigated through various pages, maybe 8 pages, including the reverse and back and forth and everything, while the person who used the B version of the website navigated through only 4 pages. Okay, and then also this person left the rating only 3, while shopping experience rating, while this person left the shopping experience rating 5. Both ultimately converted. That is the final thing. Both purchased their laptop. But it is clear that for this customer B, his journey was very smooth. So thereafter, whenever time comes for deciding the final design, then B design is preferred. The only catch in this all discussion, and that is that important catch which even if I don't speak, you have to remember that just by 2 customers things are not decided, but a large number of customers for which say 50,000 customers are there, maybe 20,000 or 25,000 are shown website version A and 25,000 are shown website version B. And then it is statistically decided that which version gets a quick conversion and which version gives a better customer experience, and that version is kept. Okay, so this version, that number of visits, number of clicks, or sometimes number of page visits required before success, that follows geometrical distribution. Now that is clear, because so here the customer just logged in. Now as soon as he logged in, he will not make immediately purchase, right? So next visit will be to some page where he will find laptops. Now in the laptops, he will find several options, Dell, HP, Lenovo, and so on. So he may choose one brand. So now he is on HP. Then he will find only HP options now. But in HP also there may be several options. There may be a high-end gaming laptops to a simple office laptop to even entry-level laptop for kids and so on. So he will still visit few number of pages, but that number of pages would be less compared to here, because here he has to visit all pages of Dell, all pages of Lenovo, all pages of HP. So that number is large. Now he is visiting all pages of HP, but that is only that all HP gaming pages, all HP office laptop pages, and all HP entry-level laptop pages. Now he has selected that I want office laptop. So in office laptop there might be maybe 10 models. So now there are 10 pages he would like to go. He will choose that my budget should be less than 50,000 rupees. So now in less than 50,000 rupees there may be only 4 models. So he will visit only 4 pages to evaluate them, and then he will choose one particular model. So as his customer journey moves further and further, you can see that in each next click he has to visit less number of pages. So in A/B trial, this is important thing to remember, that the number of pages which the customer is going to visit goes on changing according to geometric distribution, right? Okay. Then similarly, this is quality control, that the probability that ith item on a production line is defective can be modeled with geometrical probability. Now even that is clear. Suppose there is a sample of 1,000 electronic items, and you have decided that you will do quality control by checking every 10th item, right? Because you cannot check all 1000 items. No big company can afford to do that. So they randomly pick the samples from the entire population. Because if it is a multinational, say, company who is producing keyboards, then it is possible that that company has produced maybe 1 million keyboards. So if they try to quality check all 1 million keyboards, then that would be completely infeasible. So what you have to do at that time is you have to select a representative sample from that 1 million keyboards. Say 10,000 keyboards are taken, and then 10,000 keyboards, if you find them for different, say 10,000 are taken from different batches. So 1 million keyboard, suppose they are produced in 100 batches. So maybe 1,000 are taken from first batch, 1,000 are taken from 10th batch, 1,000 are taken from 20th batch, 1,000 more are taken from 29th batch, and so on. And they are all collected together. So the sample of 10,000 keyboards is corrected. Now you are checking that how many of them are defective. Then obviously initially the number of defective items would be very large, because suppose 10,000 also you divide it into small batches of 1,000. So when whole 10,000 sample is to be checked, then from first 1,000 batch, this many were found to be defective, say 5 were found to be defective. But now 9,000 only are left. So each batch size would become less. If I divide again into sample of equal 10 samples of equal size, then there will be only 900 in each sample, right? So as a result, what will happen? That among 900, again suppose 9 are found to be defective. Fine. So now here 1,000 are checked, here 900 are checked. So how many are left now? 8,100. Now among 8,100, a sample of 810, that is chosen out, and from that suppose 8.1 are defective. Now 8.1 are defective means 8 are defective. Okay, so then even they are taken out. So 1,000, then 900, then 810. So that means nearly 2,710 they are removed. So now how many are left? Only 7,300 are left. So obviously if your sample is only becoming smaller and smaller, so then the number of defective pieces found from each 1,000 sample taken from that remaining keyboards, that will also have less defects. Okay, so as a result, you will find that the defective items can be modeled using geometric distribution. Okay, so similarly in biology, the length of actin filaments follow a geometric distribution. Now this is a domain special thing, so even I do not know much about this, but actin polymerization concerns the hydrolysis of ATP into ADP, and at each step in the process, an actin monomer, polymer is several, polymer means poly means many molecules, and monomer means a single molecule. So single molecule keeps on adding, okay, and goes on forming a chain. That is called polymerization, right? That much everybody knows. So an actin molecule may either add to the existing polymer or it may fall off. But that predictability can be modeled using geometric distribution. So that means if the polymer is short initially, then the chances of actin monomer joining is high. Then as the polymer has become slightly longer, the chances of actin monomer joining with that slightly longer polymer is slightly less. But as the polymer has become very long, somewhere here, then the actin monomer, new monomer molecule, that has less probability that it will be able to join. Okay, so chances of polymerization goes on decreasing geometrically in this biology experiment. If you are in sales, then you have to you can use geometric distribution to model how many attempts will be required before your sale will end in success. Because I told you that the most important difference between this that is binomial and this that is geometric is here you are trying to model what is the probability of a successful event, while here you are trying to model how many attempts will be required or how many trials will be required before the event becomes successful. So emphasis is totally different. Okay, in both ultimate goal is for event to become successful, but here your emphasis is on how many trials are required. Okay, your emphasis is not on probability, but your emphasis is finally how many trials will be required before you make a successful sale. That is also called conversion. Okay, so marketing people know how difficult it is to convert the prospective client into a paying customer. Okay, so they know that maybe there are 20,000 maybe there are 200 visits to 20 clients. That means each client is visited 10 times, so total 200 visits are made. Then among 200 visits, suppose only 2 visits are becoming successful. So what is the probability? Probability is 2%. Okay, then they model that probability distribution using geometrical equation, and they find after how many visits will I get my first conversion. So suppose a new management intern, a trainee has come and joined the sales team, then he should not be frustrated that he is not being able to convert. If you give him clear idea that see dear friend, our probability is itself 2%, so you put in this equation and you find this, that how many trials would be required before you get your first success. Okay, so that is how you can use geometric distribution in marketing. In welding, one way to test weld strength is to load the welded joint until they fracture, either in the weld or in the beam. That distribution can also be used to model how many joints are loaded because before the first beam fracture occurs. So here, what is the successful event? The fracture occurs in the beam. Okay, so for that, as you go on adding the joints, in each next step, more the number of joints which are required to be added, that goes on decreasing. Now that is also clear because you have already added this much load. So then again this load. So as you go further and further, now the number of that joints which you want to add, that will be less. Okay. So where the fracture will occur, how many joints. So suppose on this axis there are number of joints. So then somewhere here the strength, this is the probability of non-fracture. So somewhere here the probability of non-fracture becomes zero. That means it is the first event where the fracture has occurred. Okay. So you will say that these many joints are, say here for safety, you don't allow so many joints in the beam. You just for safety say that these many joints are enough. This many. So a beam, that is one piece of beam, second piece of beam, third piece of beam put adjacent to each other. How many such joints are allowed without compromising the structure safety? That can be found using geometric distribution. Now, a safety engineer studies industrial accidents in plant, and he suspects that 40% are caused by employees who are not following the instruction. Okay, so that means he says that what is the probability of accident occurring due to employees' mistake? So then that is 40%. Okay, then to test his theory, he would make a big pile of all accident files which have occurred in the factory, small or big, all accidents in last maybe 10 years, and he would just randomly select. So that randomly select any one file. Okay, and if in that file it is found that the accident has accident report. So it is if the report says this accident occurred due to equipment failure, he will put it and randomly select another. This accident occurred due to maybe excessive pressure because the pressure gauge failed. Now that is an automated pressure gauge, so that is also not employee mistake. He will put it and he will pull the third, and so on. And ultimately, in some maybe 40th attempt, okay, or not 40th, but say fourth attempt or maybe third attempt out of entire pile, he finds one report which says that this accident occurred due to employee's negligence. So then he will say that that is a success for him because he is trying to find which event, the accident which occurred due to employee's negligence. Okay, so to test the theory, accident reports are randomly selected until one is found that is caused by employee who is failing to follow the safety procedure. So then the probability is counted out of 10. If you got that accident report in maybe out of 100, you got that in for 40, then you say that 40% of the employees are found 40% of the accident occurred due to employee not following instruction. That theory is correct. And then you can model that after how many experiments the first experiment due to employee negligence will occur. So you buy this geometric distribution and you find that after every maybe 30th accident, you find one accident in which the accident occurs due to employee's negligence. So then you can make it a kind of standard operating procedure that as soon as maybe 20 accidents occur and among them none of them was found to be due to employee negligence, then you will alert your employees that it is the record in our past record says that after every 30 accidents there will be one accident which will occur due to employee negligence. 20 have already occurred, none of which was due to employee negligence. So now the probability of an accident occurring due to your negligence are higher compared to the probability of occurring an accident due to maybe equipment failure. Okay, so then you can use that. Correct. Now similarly, there is a cephalogist. A polling employee wants to find out how many people wanted independent, and for that he will just randomly go. That is what is called exit poll. Exiting a polling people, he will just randomly go to a polling station and ask at random people who are exiting the after polling that. Did you vote for independent candidate? Did you vote for independent candidate? Okay, like that. Suppose the probability of voting for independent candidate is 0.25. That is, he is already told that thing, that the probability is 0.25, and it is possible to calculate that. Then you can use geometric distribution to find how many people will be required to be asked before they actually find a person who voted for independent candidate. Okay, so otherwise what will happen, very few people vote for independent candidate. So if he asks just 10-20 people, then maybe one person voted for Republicans and another voted for maybe Democrats, like that. But 10-20 is not a good sample, but if he knows the probability, he can use that probability in this equation and he can find plot this kind of geometric distribution. So here somewhere he finds that based on probability 0.25 of voting for the independents, this kind of geometric distribution is obtained, and here the first success is obtained. So that means that I may need to do this many trials. Okay, so maybe I may need to ask 270 people, 270 people before I find one person who has voted for independent candidate, right? So this is also an application. Now the cephalogists are in very high demand in most of the democracy. In India, there is one Mr. Prashant Kishore, who has now himself turned a politician. In US, the legendary Nat Silver, who has predicted 8 out of 9 US president elections correctly. Now that is a phenomenal record because now you are understanding that the prediction is a hazardous task. 8 out of 9 times in past 9 elections he has correctly predicted the president. Now of course I think in latest election he was predicting for Kamala Harris, and I think, was wrong because Donald Trump was elected. But that is a different thing. So still, the record would stand as 7 out of 10, which is also a phenomenal record. Anything above 60% in this kind of prediction business is a phenomenal record. Okay. Now, hypergeometric distribution is just like the geometric distribution, but it is skewed or tailed on one side. So I'm not discussing it. Okay, let us discuss because some example is also taken. Many examples are taken, in fact. Okay, so let us quickly discuss. This is the mean for that hypergeometric distribution, and this is the equation for standard deviation. As I said, these are just purely given for information. Yes, somebody who is extremely mathematically inclined can do that. Similarly, this is that combination symbol. So this is combination kx, this is combination n minus k, n minus x, and this is combination capital N, small n. Okay. Now, what is the use of this hypergeometric symbol? Then one is this use, and this is important. So please pay attention. I am going slowly here because this sampling without replacement and sampling with replacement, both these are very, very important concepts. So we want to talk about sampling without replacement because that is the example of hypergeometric distribution, but we cannot directly go to sampling without replacement. So we are first deciding sampling with replacement. Okay. Now see, this is the situation. Now these are 10 numbers. So 10 colored balls are there, or maybe 10 balls who are numbered also on them. And you are taking one out of that container. So this is my population, this is my sample. You have taken 5 out. Now you are doing second experiment. Okay. But at that time you again put this 5 inside. That is the meaning of with replacement. So what is that probability that first ball is numbered 5? Then it will be 1 upon 10 clearly. So that is 0.1. Now after my experiment is done and I have pulled 5 out, if I again put it inside, then what is the probability of getting 5 or any number, 8 or any number again? Then again still it is 1 upon 10 because I am taking 5 out, but I am not disturbing the original population because I am putting it back. With replacement means I am putting it back. Okay, putting it back means not necessarily the same 5 back, but I am putting another ball from here, which is also numbered 5. So I am making the population as it is. Okay, that is the meaning, right? So then probability of taking first 5 is 1 upon 10, 0.1. Probability of taking 5 next time is also 0.1, and the probability of taking any other ball, say number 7, that is also 0.1. Okay, now 7 and 5 are taken out, but again, just like 5 was replaced, I am putting one 7 number ball from outside. So this population is unchanged, and therefore now I am pulling out 10, but its probability is also 1 upon 10. And now I am pulling out these 10, and then what is 10, 7 and 5 are taken. Okay, another 5. So then it's 5 again. So then its probability is also again 1 upon 10. So you are understanding that this is actually a uniform distribution. This is not geometric or hypergeometric. This is this kind of distribution because every time the probability is remaining same. So you should remember that sampling with replacement, that would become a case of uniform distribution, right? Now sampling without replacement. Now think about that. Here 5 I could pull 2 times. You can see here I pulled 5 once, and here there are 2 5, right? Because I said that first 5 is taken out, but somewhere from outside you have put another ball which is numbered 5. Okay, so you can take the another 5 also, and still from outside you have to put another ball with number 5. Okay, that is the meaning of with replacement, right? So it is not necessary that you are putting the same ball which was taken from outside back in, but you can say that another, or you can say that this population is kind of infinite reservoir of balls. So as soon as something is taken out, a new ball is respawned in the terminology of gamers here. Okay, but that means first 5 is taken with 0.1, next 5 is taken with 0.1, and if I go on with repeating this experiment endlessly, then what will be the probability that 5 ball will be taken? That it will always be 0.1. So in that case, that means that distribution is uniform distribution, right? So with replacement, uniform distribution. But now think about this lower diagram, this diagram. Now here without replacement. So I have taken first 5 out. Now that means that only 9 balls remain like this in this picture, correct? Now from which, so first 5, its probability was 0.1, correct? Now what is the probability of getting 5 again in this picture? Then 0, because now there is no 5 at all. And what is the probability of getting other balls also? Say 7, then that will also not be 0.1 because now there are 9 balls. So the probability would be 1 divided by 9. Here it was 1 divided by 10. Here it will be 1 divided by 9. So it will be slightly more. Okay. So probability would be slightly more compared to this case. So that is the case. Now if I take 10, so at that time here now only 8 balls are remaining. When before taking this 10 out, 8 balls are remaining, that you can see. So the probability is 1 upon 8 for taking that 10 out. So that is even more than this probability, like that. So as each ball is taken out without replacement, the probability of having next new ball, that is unrepeated ball, that goes on increasing, and the probability of getting the same ball drastically drops to 0 because this container is such that each ball is having only one single instance, right? So as soon as 5 is taken out, now there is no 5. As soon as 7 is taken out, now there is no 7. As soon as 10 is taken out, now there is no 10. So the probability of getting next 5 or next 7 or next 10, that would be 0. But for each next ball which is being pulled out, the probability in fact goes on increasing. This is 0.1, okay, 1 by 10. This is 1 by 9. Okay, this is 1 by 8. This is 1 by 7. So as the denominator goes on becoming smaller and smaller, the probability goes on increasing. So that is also a geometric, hypergeometric distribution. The only thing is it will not be, yeah, it will be this part, okay, this part that you can see. That probability goes on increasing with each experiment. So it is a hypergeometric distribution, correct? Now this estimating the population of animals in a particular type of capture and capture example. Now this is a experiment for protecting biodiversity. You may have encountered that kind of sentence that this species is in danger, or only this many living creatures of this fish are existing. Now the question is who goes to count them and how to count them. So this is what is the method used to count, estimating the stock of particular breed of fish in the lake. So first, a known number of fish K are caught and tagged. Before you want to give permission to the fisherman that you can fish this a particular species, you have to first measure that whether there are sufficient number of that species in the lake or not. Otherwise, the fishermen indiscriminately fish out everything, and the number itself was right from the beginning less. So then in that case, it would be problematic. This is one more application of data science. Not only that, fishermen nowadays get live streaming information about the fish stock before venturing into the sea, where the fish stock is and how many fishes they are likely to find. Because think, fishing is a costly endeavor. You take your boat into the sea. Now there are how many directions in which you can start hunting for fishes. And earlier fishermen had no guidance. They had to use their luck only. And there are practically infinite directions in which they can take their boat. Many times they would not find any fish there. But now, using satellite images, it is possible to get an estimation of stock of fish. Okay, and then the fishermen are directed in that direction. And people have made a business out of that. There are only rare, maybe I think 5-6 firms who have made a business of this kind from data science. Okay, all over world. So they are in huge demand. So if data science is there in your life, at some places where you never even thought that it is there. Okay, so suppose if you want to estimate that one particular fish, say F, is how many are present in the lake, then first a known number of that fish, say K, are tagged and caught and tagged in a sample. Tagged means some dye is applied so that they can be recognized second time, right? And then they are returned to the lake. So suppose you have taken 20 fishes of that species and applied some identification mark on them, and then they are returned to the lake. After a period of time to allow for remixing of the stock, but not breeding, just that means just allow maybe around 1 hour so that they remix again. That is the tagged and untagged fishes, they remix again. Again, N are caught. And suppose for simplicity, I say that here 20 were caught and here also 20 are caught. And again, the number of tagged fishes are counted. Okay, so then the maximum likelihood estimator of that N is Nk divided by X. For example, suppose that 20 fishes were caught, tagged and returned to the lake, and subsequently 20 again are caught. So first 20 were caught, tagged and returned to the lake. Next again 20 are caught, and they were checked for tag, and it is found that 5 are now this time having tag. So this X is equal to 5. So then how many, what is capital N? That is the total number of that stock in the lake. Then that is Nk divided by X, or that is N is here 20, K is also 20, and X, the new tagged fishes found in the second sample, they are 5. So then 20 into 20 divided by 5, 400 divided by 5. So you can say that estimated population of fish of this type in the lake is 80. Now that is almost called endangered. So you have to prohibit fishing to the fishermen, or you have to, if fishermen are sincere, then you have to tell them that if this type of fish is caught in your net, then you again free it into the lake because it is endangered. Then there is another experiment, now which we are going to do later on. So at present, just don't worry. But these contingency tables are required in chi-square test analysis. So what is that chi-square test? We will see whenever it is required. But for that, how to make this contingency table, that requires cross-tabulated count data, and the such cross-tabulated count data is calculated using this kind of hypergeometric distribution. So this is a real important application in data science point of view, because you will see that that chi-square test is required so many times in data science, and at that time this contingency table you have to make. So indirectly, of course, we don't even, most of the person who are working in the companies, they at that time do not even know that they are indirectly using Fisher's exact test. Otherwise, you search for this Fisher's exact test and you will find some very interesting information. But many people don't even know that when they are making contingency tables, they are using Fisher's exact test. And still many do not know that actually Fisher's exact test is based on hypergeometric data distribution, probability distribution. But that is fine. You should be able to conduct the chi-square test. That is enough using program. But here my duty is to show you that things are built up slowly in data science. It is a science, just like our physics or chemistry, they did not build up overnight, right? So some scientists contributed basic principles, others developed them further and further. Like that, in data science also, there is a contribution of thousands of statisticians, data scientists, and machine learning engineers and so on, right? In next lecture, we want to discuss about this. This is also some statistical distribution only. Some of these are already covered. For example, normal is already covered, uniform is already covered. Then this is Gaussian, that is also already covered. Then binomial, I think somewhere was there. This is beta binomial, which is almost like binomial. This is binomial, right? So that is also already covered. But some are new. Okay, for example, this is Poisson distribution. Then this is Pareto. Then this is Cauchy distribution. So some of them which are required for data science, we will do in next lecture. We will not do all, so don't think that I am teaching some unnecessary thing. We will do only some 3 or 4 of these which are used so frequently in data science. Okay, so that would be in the next lecture. Thank you and see you in lecture. I think that will be 15, right? Yeah, this is 14, so that will be lecture 15.